Our big result so far is called the work kinetic energy theorem, and it says if a system is behaving as a particle, in other words, moving between some initial and final state without compressing or stretching or rotating in any way, then the net work done it by all external forces, that's what net means, is equal to the change in kinetic energy of the particle. We're now going to generalize this result very slightly in a way that's going to help us be able to address more complicated systems later on. And the idea is, instead of considering just a single particle, we're going to imagine a system consisting of several things that are moving like particles. So here's an initial state consisting of 3 blocks, and we're going to imagine in between some initial and final state there are forces acting on each of these 3 blocks. External forces are reaching in and being applied to them in between the initial and final state. And those blocks might even be displaced by different amounts. Maybe this red one is displaced by a smaller amount, the green one a larger amount. And what's true in this case is that if we just apply the work kinetic energy theorem to each of the particles individually, we can add up the net work done just on particle 1 and just on particle 2 and just on particle 3 by external forces. And if we add up those 3 equations, the left-hand side will define what we mean by the net work done on the system. It's just the works done by all forces on all of the different parts of the system added together. That's what we mean by the net work done on this more complicated kind of system. And the sum of the changes in the kinetic energies of all the pieces is what we're going to mean by the change in kinetic energy of the system. So the kinetic energy of the system is nothing more than the sum of the kinetic energies of the parts, and the change in it is the sum of the change in the kinetic energy of the parts. So not only is the work kinetic energy theorem true for a single particle, but it's also true for systems of particles as long as we regard all of the external forces all of the forces acting on parts as external. So we'll apply that later. We're now going to turn to these more complicated kinds of systems, systems for which the work kinetic energy theorem doesn't apply. In other words, that last condition is not met. Let's think about a system consisting of several objects connected by some forces that we're going to regard as internal forces to the system. For example, here are 2 objects and they're connected by a spring force, but I'm not going to regard that spring force as external. In other words, it's applying forces to both of these particles, or both of these pieces within the system. But the spring force on this piece right here, we're not going to regard as external, but rather internal, and same with the other side. And the individual parts of the system can be displaced by different amounts, but for these more complicated systems, we're only going to consider, or we'll only be interested in, the work done by external forces on the pieces. In other words, in going from the initial to final state, it's certainly true that the spring force does some work on each of the pieces of the system as it's moving, but we're not going to consider that spring force as long as we're not going to consider the work done by it as long as it is considered to be an internal force. And the reason for that is because we'll be interested in things like containers of molecules of gas that might have a huge number of molecules inside the container. And each of those molecules is exerting forces on the other molecules in the container. There are so many of these forces, we just can't keep track of them. And so there's no way we could ever calculate the work done by those internal forces on each of the molecules as it bounces around the container. So we're only going to consider work done by external forces, maybe forces like the forces of the sides of the container on each of the molecules as they're bumping around in there. We're also going to calculate the work done in the following way. If there's an external force acting on this particular piece of the system as it goes from here over to here, we're going to calculate the work by using, there are different displacements here, and the displacement for calculating the work done by an external force acting on this one is the displacement that it undergoes from the initial state to the final state. So we only look at the displacement of the location at which each external force is applied when we're calculating the net work done on the system by external forces. That's good to keep in mind as our systems grow in complexity. So what we're going to develop now is a few examples that show that if the system isn't rigid, systems of this type, we might be able to do work on it by external forces, and yet the system will not gain kinetic energy. And so it's definitely in violation of the work kinetic energy theorem. So we'll be back to do that in a moment.